Welcome back, guys. It's great to be with you again. Today we start with the optimization problems, basically. We start with linear optimization problems. Then we go for convex optimization problems. Of course, the main objective is to solve the support vector machine optimization algorithm. So all the steps we are going to approach from this point on are basically devoted to solve the support vector machine optimization algorithm. So we start with an outline about optimization problems. We're going to define what is an optimization problem, the main types. Actually, we are going to deal with two types in this course. Of course, there are some others, but we are just devoted to those two because they are the most important, for us at least. Okay. The first is, of course, we're going to remember how linear optimization problems work. We're going to see some examples, an overview about the primal versus dual forms. Also, some points on the graphical interpretation of primal and dual problems, how we can use Lagrange multipliers to build up dual forms given if we're given the primal form of course, as a starting point. And afterwards, we're going to solve nonlinear but convex problems. Okay. This is the definition of an optimization problem. Of course, I'm going to define in terms of minimization, but we could define in terms of a maximization. Doesn't matter. What matters is the form or the elements we have. Consider we have a minimization problem of some function f0 in terms of x. This function f0, as you guys can see here, receives n elements, n parameters, and produces a real number. It is mapped on the real line. This is our objective function. Okay. Here we have the constraints, those fi functions that also receive x as input and have like some bound defined over here. I'm just defining this form in terms of less than or equal to, but it could be equal to or greater than or equal to, or just greater than or less than, or smaller than, of course. All those functions here, fi, they also receive n elements, n variables, and their map goes, of course, to the real line as well, and those are our constraints. They define like bounds for our problem. Okay, they tell us what are the conditions that our problem must satisfy while solving the objective function. For example, I have like some area to grow corn and oats, for example. I cannot pass such a limit of land that I have available. So that would be one of our constraints, for example. Or maybe an amount of money I have to invest in my project. So that's also a constraint. Okay. All of those constants, b1 to bn, are constraint bounds. As you can see here, they define some bounds. For example, this could be like the amount of money I have to spend less than or at most be equal to some amount of money. This could be the amount of money my constraint function has to satisfy. As you might see, I'm considering here like m constraint functions. The point I apply here, the point x, is my input variable, to speak. Okay. In this case, consider x to be a vector. So a vector with n elements, as you might see over here. They contain, this vector contains the optimization variables. Okay, so a set of variables I can adapt to solve my problem, while of course meeting the constraints, while satisfying the constraints. So this is the set of variables we can modify to optimize our problem, to find the solution, the final solution for our problem. Going to the next, consider we were given like a vector x star. This is assumed to be the optimal solution for our problem. Okay, this optimal is the set of values for which the vector x provides the best as possible solution. In this particular scenario, that is the same as saying that if we apply x star into f0, which is my optimization function, it will produce the smallest as possible value, or maybe equal, to every other application of z. Suppose z has like any other possibility for x. Okay, of course, satisfying our constraints. Of course, I need to come up with a given z over here to be just like a candidate solution. And suppose my constraints were satisfied, as seen over here. If I take that particular value for my vector and apply in f0, my x star is still better. It minimizes, as you guys can see here, for any other possible solution we can apply. This is the case of a minimization problem. We could rewrite all that formulation in maximization form. Of course, if I take this as my primal problem, the dual problem would be a maximization problem. Going to the next. At this point, we are just interested in two main types of problems, of optimization problems, to solve the support vector machine problem. We are interested in starting with linear optimization problems because that will provide you the foundation for a next step, which is nonlinear optimization problems. Most especially, we are worried about convex problems. That's actually the case of the support vector machines. It's a nonlinear optimization problem, actually, in which my objective function is convex. However, you can have like some other types of problems in which I've got some quasi-convexity or a completely non-convex optimization problem. So at this point, we are just going to take a look at those types and be aware of the possibilities, okay? This is a linear optimization problem. That's basic. My objective function must be linear, and every constraint must also be linear. Suppose this function f0 is linear, and every function fi from 1 to m is also linear in terms of x. In this scenario, you've got something like that. You've got like, okay, here I have my linear surface defining my objective function. Okay. Here I have some input variable x1 and x2 forming my vector x. So it's a bidimensional vector. And here we have the application of f0, as you can see in this axis. Here we've got 4 constraints, one linear constraint, a second linear constraint, a third linear constraint, and a fourth linear constraint. And by being like smaller than or equal to those elements defining my constraints, what means in this scenario is the same as being inside this region. Just suppose that at this point, because it's going to be easier as we go to other examples. So suppose we are just inside. Of course, this is a linear constraint, another linear, and another linear in terms of x1 and x2. And my objective function is linear. That is the case in which my problem is a linear optimization problem. Going to a next problem. Here we have our objective function is non-linear, like this. Take a look. This is a non-linear optimization function. Okay, objective function. However, our constraints are linear. One constraint that's linear, the second linear, the third linear, and the fourth linear. This is a nonlinear optimization problem in which all constraints are linear, but my objective function is non-linear, but in this case it is convex. Actually, this kind of problem is not difficult to solve. We can use like a bunch of things, strategies to solve this problem. This is in fact the basic problem we are going to face with the support vector machines. This is the most basic problem in our scenario. Okay, we're going to see that in the future. Just keep in mind this shape, these shapes actually. Going to the next case, here we have another nonlinear problem. Our objective function is linear. Two, are linear, but this third constraint, take a look, goes like this. It's nonlinear. If one of those functions is nonlinear, my problem is nonlinear by default. Okay, here it's not that difficult to solve this problem, because if I want some maximization or minimization, I can just map this into my objective function using Lagrange multipliers and find some maximum value or minimal value. Okay, but of course, depending on the problem, this becomes more and more complex. Nonlinearities bring more complexity to our problems. For example, this will be, of course, much more complex to solve, because here we have two linear constraints. Those are easy, but this one is a third nonlinear constraint with a nonlinear objective function. This nonlinearity of my objective function, this nonlinearity of my third constraint makes this problem more difficult. I can assure you that it takes like more effort to solve this problem. We need like a different tool set to find a solution. It's not that easy, you know. Going to the next case. So just suppose this scenario. We have nonlinearity in terms of this constraint. It's a single constraint, but it's a non-linear constraint. However, it forms a convex set. What's a convex set? If I take one point inside this set and connect to another point inside the same set, any other point, the line connecting both points lies inside this feasible region. Consider I'm interested in this feasible region, in this region defining the set of possible solutions I have for my problem. So any solution inside this or equal to my constraint is okay. I can accept it. So you can take a look here. It's not that complex to solve this problem if my objective function is linear, as you see here. It's a surface, a linear surface. I just need to map this constraint into my surface over here, like this, and then I can solve Lagrange multipliers. Lagrange multipliers is going to map this for me. As this is a linear surface, of course, my maximal and minimal values will be touched by this constraint. Okay, so it's not difficult to find some maximal, some minimal value over here. Of course, we can go to more complex problems. For example, that non-linearity may bring like some issues to solve my problem, and we're going to see that. However, if my feasible set is still convex, is still every point inside my feasible set can be connected to any other point inside the same set, just using a line, and that line lies inside the feasible set itself. That's what convexity in terms of sets means. For example, to go back over here, if I take one point over here inside my feasible region and connect to another point inside the feasible region, the line touches an infinite number of points, but all of those points are inside the feasible region as well. That also happens if I take the boundary, because I take one point on the boundary and another point here on the boundary, I will be exactly on this boundary line. So any solution that my line crosses is inside the feasible region. Just assume we are inside this feasible region. I could be outside, but in this case, I'm just assuming we are inside. The same doesn't happen here. If I take this point over here and try to connect with a line to a point over here, I'll be crossing outside the feasible region. That means this set is non-convex, or is not convex. So I take this point and connect with using a line to another point over here. Take a look. The line will be crossing outside the feasible region. That means this is not convex. Those are much more complex problems to solve. Okay, every time we have like some sort of non-convexity, it becomes more complex. The same can be seen here. I take this point over here and connect with a line to a point over here. I'll be crossing outside the feasible region. That means this is not a convex region. Of course, here, any pair of points I connect with a line, the line will be inside my set. So this is a convex set, defining my constraint. Okay. Of course, this kind of problem, convex constraints or convex feasible region defined by, in terms of my constraints, are of course easier to solve, much easier actually to solve. Okay. Of course, if our feasible set is convex, and let's suppose my objective function is nonlinear, however, it is convex. That is exactly this scenario over here. Let me get back. Exactly this. This is the scenario we have for the support vector machines. Here I have a convex feasible region with defined by my constraints, but a non-convex, but a convex function defining my objective function. However, it is nonlinear. By convex in terms of function, it means that if I connect one point here with another point of my function, this line will be above my chart, will be above my graph over here. Connect this point here with this point over here. The line connecting will be above, will be in the epigraph of my chart. Okay, so if I have like this, which is like x to the square plus y to the square, I can connect 2 points, and those 2 points will be up. Okay, will be we say in the epigraph of my chart, will be above my surface. That's what mean convexity in terms of objective functions. So that is exactly the problem we are interested in solving. You know what's quite interesting is this. If our objective function is linear, I could solve using Lagrange multipliers, and that becomes easier to solve. That's exactly what we did here. For example, I can just map my constraint here, and knowing my objective is linear, I can take what is the maximum and the minimum, or just find all critical points over here and solve my issue, my problem. Okay. However, if I have a problem like this, in which my feasible region was defined by linear constraints, however, my objective function is convex. Take a look at this. Where is the best solution? It is probably inside my feasible region. So if it's inside, I cannot just map those constraints into my objective function and solve Lagrange multipliers. Because by solving Lagrange multipliers, I would find some point touching the constraint. It would be the same as projecting the constraint here like this, then this, then this, and then this, and solving for one of those points. However, the solution is much more inside this feasible region over here. That means I cannot use Lagrange multipliers. I need some way of walking inside this region. We call those methods, we refer to those methods as interior point methods. That's what we're going to use to solve the support vector machine optimization problem. Okay. So going to a next case, another type, just suppose a problem like this. This is just to get just to remember how to solve. Our objective function is linear, but our constraint is nonlinear. Is it difficult to find this, the solution for this? It's not. It's Lagrange multiplier. Lagrange multipliers will allow us to project the constraint over here like this and find some maximal or minimal value for points touching the constraint, okay? Touching the projection of this constraint over here. That's not difficult to solve, okay? What's really complex is when we have some nonlinear objective function and nonlinear constraints, and both are not convex. Both are not convex. However, in our case, using approaching support vector machines, we are worried about nonlinear optimization functions. However, they will be convex, and we will be worried about constraints that are only linear. So just to get back, this is how our support vector machine problem look like. An objective function that's convex, it is not linear, it is non-linear, of course, but it's convex, what means that I have just a single minimum solution over here. However, I cannot just project those constraints onto my function, my surface, because that would never provide a solution for me, such as using Lagrange multipliers, because my solution lies inside this region and not on the constraints, okay? So that's what we are worried about at this point. So next video, we're going to start with some foundation on linear optimization, and then we go for more complex problems. See you guys.